All right, well, hello everyone, and welcome to the next section of the course, which is section 5, which will be mostly chapter 5 material, which is the section on what we call stereoisomerism, which is really just another in-depth look at three-dimensional shape of molecules, some of the concepts that are tied up with that, concepts of chirality, and things that are consequences of those concepts on our organic molecules. So we're just going to go take a look at sort of back to the idea, and this ties in with the earlier ideas that we discussed about isomers. So we had constitutional isomers. Those were different isomers that had the same chemical formula but different connectivity of atoms. And we talked about those quite a bit right at the very start of the course. Now the other kind of isomers that we introduced a little bit later were stereoisomers. Oh, we didn't quite use this term for them at the time. We talked about conformational isomers. That is, molecules that differed only about the conformation around a carbon-carbon single bond. So different rotations, ethane, butane, cyclohexane, all of those kinds of isomers that we talked about at the time. We also can introduce another kind of isomer called a geometric isomer, and this occurs specifically around carbon-carbon double bonds. We have E versus Z carbon-carbon double bonds, and we'll talk a bit more about that later, about how to assign E versus Z, its priorities, and we'll talk about that in the next video. But here, this is something you would have to break a double bond to interconvert between these two stereoisomers, and so those are distinct isomers all in their own right. And again, the nomenclature we use is E versus Z, and we'll address that in the next video. And so we'll carry on with this here. The other kind of isomer that we can now imagine here is something that we call configurational isomers. And again, the interconversion of those isomers involves breaking a bond of some kind, not a double bond, but breaking a carbon hydrogen or a carbon single bond of some kind. And these kind of fall into two categories. One are enantiomers that have non-superimposable mirror images, and the other are diastereoisomers that are not mirror image related. And so we'll explain what these terms mean in the next couple of series of videos in some more detail, but this is where we're going in this particular section, is to look at these kinds of isomers. So let's focus on the configurational isomers, and what we want to do is describe how we get to these particular types of isomers. And so what we want to look at are what we call here the distinction between achiral and chiral objects, and we'll look at this in more detail in a minute. So an achiral object is any object that has an internal plane of symmetry and has superimposable mirror images. And so this is a large variety of objects that are around us, almost anything that we can imagine. Or many things that we can imagine, like a ball or a stick or other kind of like just regular everyday objects. We'll relate this to molecules in a minute as well too. But these are superimposable mirror images. We want to distinguish those from what we call chiral objects. And these are objects that have lack an internal plane of symmetry. They lack an internal plane of symmetry, and they have non-superimposable mirror images. And so those objects that have non-superimposable mirror images exist as a pair of enantiomers. And now this is a concept that applies to any kind of object, not just organic molecules. And so one of the more common examples that we would have of this would be something like our hands. So our hands can exist as chiral objects. We have a plane of symmetry down the center of us. So if I hold my hands like this, there's a plane of symmetry right down the center of me. And so they're mirror images of each other. They're mirror images of each other, and that would be just like there was a mirror running down the center of me, and I would have my two thumbs close to each other. So in a mirror, what the close objects appear close and far objects appear far. So my thumbs would be close to each other. My pinky fingers are farther away from each other in the mirror. And these two objects can't be superimposed on each other. So I can lift up one hand, I can carry it over, and I can put it down on top of the other one. And of course, my thumbs don't line up. My fingers don't line up properly. I know you say, well, okay, just flip your hand over. And so I flip my hand over, and of course I can do that, and now my thumbs line up, but of course my palms and the backs of my hands don't line up properly. And so these are objects, your hands are objects that are non-superimposable mirror images. And so if you can look around, there's a lot of other everyday objects that also possess this particular quality, so you may be able to find some of those around. So let's take a look at how this property of chirality translates into molecules. So what I want to do is try to imagine what this would look like in molecules, and we'll take a look at a couple of simple examples of what would be superimposable achiral molecules. And so here we've got a couple of molecules that are on the display here. And so what we've got is we've got here, if we take a look, we've got the red and the white, the two blue atoms here, and a red and a white and the two blue atoms there. And so these are molecules that are mirror images of each other. If there was a mirror running right down the center, the objects that are close to each other are close, and the objects that are far away will be far from each other. And so these two objects are completely superimposable mirror images. So for example, I can lift up this molecule, I can twist it around 180 degrees, and I can line up the red, I can line up the red and the white and the two blue atoms, and they all line up. They're perfectly superimposable on each other. And so an example of this may be something like, so this might be an example of that kind of molecule where we have an sp3 hybridized carbon atom can exist as a tetrahedral, and we can put a bromine, a chlorine, and two hydrogens on it. And so these atoms here, the bromine and the bromine are going away from us, the chlorines are coming out towards us here, and the two hydrogens are identical. And so I can rotate these around and make them identical mirror image objects with respect to each other. I can make them identical mirror image objects with respect to each other. They're superimposable. They're superimposable mirror images. If I just spin them around, I can put them on top of each other, no problem at all. I can line them up 100% perfectly. These are completely superimposable mirror images. They are achiral objects. They fit in that achiral objects. And so all of the molecules that we've looked at so far in this course are what we'd be best described as achiral objects, since they fall under this where they have superimposable mirror images. Well, now what about molecules that have non-superimposable mirror images? Let's take a look at an example of what that would look like. So there's two objects, two mirror image objects. If there was a line down the center of that iPad, if there was a line down the center of that iPad that was acting like a mirror, these two objects are reflections of each other. What's close to that mirror, the bromine and the chlorine are close on the reflection, and the fluorine atom is far away on the other side as a reflection of each other. And so what would this look like if we translated this into the two objects that we have on the table here? What we could do is replace one of the blue atoms with a green atom on one of our models, and replace another blue atom with a green atom on this model here. So now we have two objects. We have two objects where they're showing each other. These are mirror images. If there was a line right down the center of the table here that would divide those two atoms, that would be a mirror plane. The two green atoms are close to each other. The two blue atoms are each other. The white and white are on the top, and the red are at the back. And now there's nothing I can do with these two objects. There's nothing I can do with these two objects to make them superimpose on each other. I can spin them around so that the red and the white line up. I can spin around so the red and the white line up, but the blue and the greens don't line up. They're opposite of each other. I can flip them around so that the blue and the greens, flip them around so the blue and the green line up with respect to each other, but the reds and the whites don't line up with each other. And if you've got your model kit and you want to play along a little bit, you can see that you can do this. You can do this and play around. If you've got 4 different objects, if you built them the right way, they are they won't line up no matter how you sort of twist or turn them on the table. So these are non-superimposable mirror images. These are chiral objects. These molecules that we've drawn on the page here are chiral molecules as well. And so one of the definitions that we have then for chirality can be explained by sort of a simple definition. We can come up with a definition for organic molecules anyway of conditions where objects will become chiral. And that definition is that we have 4 different substituents on an sp3 hybridized carbon atom. Now, one of the definitions that our textbooks use is something called a chirality center. I don't really like that a whole lot personally. I think a more useful definition is a stereogenic center. But anyway, for purposes of what we're doing, this sufficient condition of having 4 different substituents on one sp3 hybridized carbon atom is sufficient for the purposes of describing an object as chiral. So let's look at a couple more examples, or another example of this kind of object in a molecule that might be a bit more representative of the kind that we've seen. Let's see if we can take a look at a molecule that would be more kind of representative of what we've seen. And so here, for example, here, for example, is a more kind of typical organic molecule, the kind that we would take a look at, where we've got a couple of different substituents on it, something like an alkyl halide. We'll come back to those in a bit more detail. So what we've got here at this blue carbon atom is we've got an ethyl group on one side. We've got a methyl group on the other side. We've got a bromine on one side. And of course, we haven't explicitly drawn it in, but we know that it's there, a hydrogen atom pointing towards the back, away from us in the way that we've drawn this particular molecule. And of course, that hydrogen atom is also present on this other molecule here. These two objects are mirror images of each other. If I draw that red line down the center of the iPad page and right where those two objects are, they're mirror images of each other. The two methyl groups are close to each other. The two ethyl groups are far away from each other. The bromines are coming towards us, and the hydrogen atoms are going away from us. So those are mirror images of each other, and they are not superimposable upon each other. You can lift one object up and carry it over and place it down on the other, but the methyl and the ethyls don't line up. The bromines and the hydrogens would, and if you flip it around, you can get the other groups to line up. But there's just no way that you can make these line up. So let me see if I can convince you of this with the model kit as well. Okay, so let me see if I can convince you that these two molecules we've drawn, are not superimposable mirror images with the model kit. And so in the model kit on the bottom, what we've got are the two models built. We've got the ethyl group here, the methyl group and the methyl group kind of close to each other. There's the ethyl groups far from each other, so we've built them identically to what's represented above on the iPad. Picture the model kit. There's the red bromine atom coming out towards us, and the hydrogen atoms are hiding right in behind, but pointing back at the table. So now these two objects are completely not superimposable on each other. I can take one of them and I can lift it up, I can lift it over, and I can set it down on top of the other object. Now, of course, the two bromine atoms line up perfectly, and the two hydrogen atoms line up perfectly, but I've got a methyl on top of an ethyl, and an ethyl on top of a methyl over here. So those don't line up. They're not superimposable. I can lift one of the objects up and flip it around so that the ethyl and methyls line up, and that's what we've just done here. But now the bromine, one of the bromines is pointing back away from us, and the other bromines is pointing towards us at the front here. So these two molecules are chiral objects. Maybe I can set them up this way here, and you can see again that they're mirror image objects of each other. Now we're looking down at them. The mirror plane is right here on the table. Two bromines are pointing towards each other. Ethyls are pointing at the top. Methyls are coming down this way. And again, I can lift this one up and over and set it on top. And of course, the ethyls and methyls line up perfectly, but the two bromines are on opposite sides. I can lift this up and twist it around and get the hydrogen and the bromine to line up, but now I've got an ethyl and a methyl over here, and a methyl and an ethyl on the other side. And again, if you've got the model kit and you want to play around at home a little bit with these chiral objects, you can see that there's nothing you can do short of breaking a bond and remaking a bond to make them into the identical objects. There's no way to interconvert these short of breaking and making a bond. If I do that, then I turn them into the same object. But if I don't, if I've got the non-superimposable mirror images, I can't easily interconvert these. And so now what we have to be able to do is to kind of devise a way to sort of talk about these enantiomers with other competent chemists. So one of the things, and we'll talk about this in yet another video a little bit later next week, but the enantiomers, we have to have a way of describing which one of the two enantiomers we're looking at, because they're chemical and physical properties of enantiomers, at least the organic molecules that we're dealing with. All of their chemical and physical properties are identical with respect to each other. They've got the same melting point, same boiling point, same index of refraction. They run the same on chromatography. You can't separate them by that method. So all of their physical and chemical properties are identical. But it is important for us to be able to tell a competent chemist which one of the two enantiomers we're looking at. Is it this enantiomer of 2-bromobutane, or is it this enantiomer? And so the next video that we're going to post, we'll talk a little bit about the what we call the Kohn-Ingold-Prelog nomenclature as a way for describing to another competent chemist which one of those two enantiomers you have.